So again, looking at this, I'm not so much, we will set them up and do the math, but I really want us to be able to look at these and distinguish. So you have this information here, so I'm going to zoom in a little bit more so we can actually read the question. But you have all the information that's in this box on the sheet that you have. What I would like you to do is get a sheet of paper or something like this so that we can kind of work this together. The problems that I put on the board here are going to be a little bit different than, or they're different problems than the ones we have in the practice. So just to kind of introduce and go through, we want to be able to identify what equation we're doing. And I will tell you, I left one off. I left one of them off, and that's Avogadro's law. And Avogadro's law is basically you can go volume over moles equals the new volume over the new moles, or it can be pressure over moles equals new pressure over moles. So there's a relationship between moles, number of moles and pressure, and there's a relationship of number of moles and volume. And I guess technically there could be a relationship between moles and temperature, but we're not going to go there. That's a more complicated one. So let's look at this first equation, first question. It says, explain what each of the following changes would do to the pressure in a closed container. So will the pressure increase or decrease? And we want to relate each of these to a specific gas law. So first one, gas molecules are removed from the container. So if we're removing molecules, what are we changing? The moles. We're changing the moles. So if we remove moles, what are we going to do to the pressure? Decrease. D-E-C-R-E-A-S-E. It will decrease the pressure. And so which one, Charles, Dalton, Boyle, Gay-Lussac, which one dealt with changes in moles? Avogadro. And I would even go ahead and write the relevant equation just so that you get used to seeing it. All right. So the second one, container size. The volume is decreased. So we decrease the size of the container. What's that going to do to the pressure? So pressure increases. And who does this one relate to? Boyle. And then the last one, we change the temperature, so the temperature's increased, but the container stays the same size. So what does that do to the pressure? If temperature is increased, yes, it's a direct proportional. So if temperature is increased, pressure is increased. The only one that's going to happen in the opposite is Boyle. And then who deals with pressure and temperature? Gay-Lussac. And then the other thing that we could look at is Charles's law. We could look at Charles's law, which relates between volume and temperature, but we were specifically focusing on pressure. So we don't see that one on there. All right, let's look at another example. All right, so given the same information up above, So let's look at this equation, this question. How many moles of oxygen will occupy a volume of 6.5 liters at 4.3 atmospheres and 275 degrees Celsius? So how do I know which one of the gas laws to use here? All right, so we have a pressure, we have a temperature, we have a volume, and we are looking for moles. All right, so we have that, we have that, we have that, and so this one we would use ideal gas law. Now, the things to notice on this one, we only have one condition of each thing. So we want to know how many moles, and we're given a volume, we're given a temperature, and we're given a pressure. Now, the only thing in ideal that we don't have is the R, but the R is given up here. Now, the other thing that you have to check for is we always need to check for what our pressure is in. In some of the problems on the test, I'm going to give you a pressure in torr, but I'm only giving you this one, which is for atmospheres. So if I would have given you in torr, how would we convert from torr to atmospheres? Divided by 760. So notice that I am giving this information right here so that you can do your conversions. All right. I just would prefer everything being an atmosphere. I like the numbers that you get with atmospheres a little bit better. So just setting this one up, I'm not really going to solve it. You can solve it if you want, just for the practice. So our pressure is 4.30 atm times our volume, 6.5 liters, equals the moles. That's what we want to know. Our R, 0.0821 liters, atmosphere. I got a little bit more room. Liters, atmosphere, mole, K, and then times our temperature. And what's wrong with our temperature? It's in Celsius. So I'm just going to show you, you don't have to do it separately. You can do the 275 plus 273 inside the parentheses. As long as you take care of that first, you know it's going to be in Kelvin there. All right. And then that's our problem. The other thing that I want you to recognize, crud. The other thing I want you to recognize with this is the units on our R value. This liter, atmosphere, mole, K, all that is for is to allow you to see what your final unit is going to be in. So we're solving for mole. That means everything else should cancel out. So we should have a liter. That gets rid of that liter. We should have an atmosphere. That gets rid of that one. We should have a Kelvin, and that gets rid of that. So don't freak out by the units. Just know that that's to help you cancel and to make sure you end up in the right units. All right. So what'd you get? So if you solve it, you should get, or hopefully we all get 0.621. I'm trusting your answer. All right. So makes sense? Do y'all see how we got there? The biggest thing is identifying the right type, the right equation to use, the right gas law to use. All right. So looking at another one. This question's a little bit more in depth. So nitrogen, oxygen, and carbon dioxide are in a closed container. The oxygen has a partial pressure of 21.0 millimeters mercury, so that's PO2. The nitrogen has a partial pressure of 50 50.3 millimeters mercury. The total pressure is 89.9 millimeters mercury. What is the partial pressure of carbon dioxide? So we want to know PCO2. So whose law is this going to apply to? That's going to be Dalton. All right. Now, the other thing on Dalton, whenever I show it, I only go up to P3, but understand you could have up to 20 gases on there if it really wanted to. I won't do that on the test. I'll do 2 or 3 at most. So we're going to use P total equals P1 plus P2 plus P3, or in this case it would be PO2 plus PN2 plus PCO2. All right. So 89.9. Also be careful on these. Just make sure, verify that all of them are in the same unit of pressure. If they're not, you need to convert to where they're all the same. So 21.0 plus 50.3 plus PCO2. All right, so basically 89.9 minus 21 minus 50.3. And what do we come up with? 18.6. All right, does that make sense? Grab you one. Thank you. Let me grab you. What am I doing with my extras? All right. We're not actually working on this yet. We're just kind of going through trying to identify what type of problem to use, what type of equation to use. All right. So going forward, looking at this next one. So on this one, the question states a gas at 200 kilopascals. So kilopascals, what is that? A pressure. And 21 degrees Celsius is a temperature, and an initial volume of 3 liters. That one actually tells you what it is. That's a volume. The pressure of the gas is increased, so this is a new pressure, so that's like a P2, as the temperature is raised to 100 degrees Celsius, so that is a T2. So we have a P1, we have a T1, we have a V1, and then we have a P2, we have a T2, and we want to know V2. So which of the gas laws are we going to use? Combine. And combined is P1 V1 over T1 equals P2 V2 over T2. All right, if I wanted to set up the equation, we could go ahead in there. Now, quick question. We're solving for volume. Do I need to change these to atmospheres before I start the problem? Why not? Because they're the same units. If they were different units, then we might have to convert something. But if they're the same units and you're not solving for that unit, then you don't have to change it. Only in ideal gas law will we have to change the pressure. So we would go 200 kPa times the volume is 3 over the temperature. It's 21 degrees Celsius, so I'm going to add 21 to 273 equals our new pressure of 300 times our volume, that's what we're solving for, over 100 plus 273. So volume 2, again, we're gonna multiply this to this group, and then we're going to multiply that 300 to this, and then we're going to divide it, and that'll give us V2. So just to kind of show you Alright, so essentially whenever you move your things around, you would have 200 times 3 times 373 divided by whatever you get, 294 times 300, and that should give you the answer. What you get? 2.54 liters. And the other thing to look at, your answer should make sense. So you should get a number, like our original volume was 3 liters. We raised the temperature, but we raised the temperature by 70 degrees or so, and then we changed the pressure by a lot. So we just need to pay attention to that. The new volume makes sense. If you got a number like a volume of 400 liters, I might question that one. Your number, this number is similar to our original, so it does make sense. All right, and let's look at another one. I think I have 2 more to look at, and then I can let you go on your own and kind of help each other and all of that. All right, this one, I pulled this one from another sheet. I just changed some of the numbers. I think y'all did this problem already. You're out ice fishing with your dad. The propane tank attached to the heater had a pressure of 5 atmospheres when you bought it and was at a temperature of about 7 degrees Celsius. As the fuel tank gets used, the pressure in the tank drops to 2 atmospheres. What is the temperature of the gas in a tank, assuming no loss or gain of heat? So we have a pressure, we have a temperature, we have a P2, so now I'm going to call that P1, and we want to know what is the temperature. So that means we have a T2, so we'll call that T1. So based on this information, based on knowing what's in there, which gas law deals with pressure and temperature only? Right here. All right. So if you pull out, basically what I'm telling you, if you pull out your givens first, it's going to be easy to identify what's going on there. So we're going to use P1 over T1 equals P2 over T2. Now, the other thing that I'll say, it really doesn't matter which pressure you put in as P1, as long as the temperature associated with it is going to be the T1, and vice versa. So I can set it up however I want, but I'm going to start with 5 atmospheres being my P1 over 7 degrees Celsius. Always convert to Kelvin, so it's going to be 7 plus 273 equals 2 atmospheres and it's going to be T2. Now, the only thing I would tell you to be careful about these when you're manipulating it, realize when you bring that 2 across, that this actually ends up being 1 over T2. So to get your final answer, you need to get the reciprocal of that. I tend to manipulate it another way, where basically I just flip my numerator and denominator here, and that gives me the answer to T2. So T2 equals 280 times 2.00 over 5.00. All right, so does that make more sense? Does everybody follow the math that I did or the steps I did to get to it? And again, I'm trying to show you more steps than most of you probably need. I just want to make sure everybody follows what we're going through on that. All right, let me make sure of how many we have left. I think we only have, oh wow, we got 3 left. 4 left. I did that many? Wow. Yeah. All right. So let's look at this next one. And again, we're just trying to identify which one it is. I'm not really worried about the answer right now. So this one, the temperature inside my refrigerator is about 4 degrees Celsius. So this is a temperature. If I place a balloon in my fridge that initially has a temperature of 22 degrees, so I'm actually going to call this T1, and I'm going to call this T2 because we are going to lower the temperature from 22 to 4. And an initial volume, that's a V1 of 0.5 liters. What will the volume of the balloon be when it's fully cooled by the refrigerator? So that's V2. So just listing, V1 is 0.5 liters. T1, 22 degrees Celsius. V2 is our unknown, and T2 is 4 degrees Celsius. All right. So which of the gas laws relates solely to volume and temperature? Charles's law. So we're going to use this equation to set it up. So V1 over T1 equals V2 over T2. And I'll make that statement again. It really doesn't matter which one you tag as V1 and T1 as long as you're making sure that the ones that go together. So we could have very easily called 4 degrees Celsius our T1, but we would have had to change the volume of the balloon to our V1. and we could have called both of those our T2. It really, you just have to make sure that the volume and temperature that go together are in the same fraction. All right, and this one's easier to solve because you're solving for V2, so you'll move the T2 up here, divide by T1. Yes? Okay. So I would treat this as a group before I divide it, or before. So I would multiply these two together and multiply these two together before I divide it from the other. Because you're taking that total and multiplying it by that. So what I would do is put that group, the 328 and the 0.0821, I would do that math first. So this one is your better answer, the 108. Oh wait, you're solving for moles?
That's what I'm thinking.
All right. So 112 times 2600. All right, so that's 2912. Do 0.821 times 328. All right, so now divide 292. Oh yeah, I am expecting a big number. Yeah, that's right. That's a heavy atmosphere, so it does make sense to me. And it's a big volume. All right. So again, I would rather y'all not work on the review sheet. You're going to have a lot of time for that. I just really want to make sure that y'all know how to get the right problem right. I didn't solve it. I'm just trying to make sure that we get the right equation first. All right. So looking at this next one, part of the reason conventional explosions cause so much damage is their detonation produces a strong shock wave that can knock things down. So basically, they produce a lot of pressure. While using explosives to knock down a building, the shock wave can also be so strong that 12 liters of gas will reach a pressure. So this is a volume. Will reach a pressure of 3.8 times 10 to the 4 millimeters of mercury. When the shock wave passes and the gas returns to the normal pressure, what will happen to what will the volume of that gas be? So this is a P2, this is a V2, this is a V1 and a P1. So we are dealing with a P1, a V1, a P2, and a V2. So what gas law only deals with pressure and volume? Boyle's law. So you're going to have P1 times V1 equals P2 times V2. All right, I'm not plugging in the numbers. I'm just going to move on to the next one. All right. So looking at this one, what volume will 4.83 moles, so this is a moles, what volume, that's a question mark, what volume will 4.38 moles of nitrogen occupy at 843 millimeters mercury, that's a pressure, and 20 degrees Celsius, that's a temperature. So we have an N, we have a P, we have a T, and we want to know V. So looking at this information, which equation are we going to use? Ideal. We're going to use PV equals nRT. Now, looking at the information I gave you in your box, what are some things we need to change? Okay. Always need to change the temperature to Kelvin. We don't need to change the R. I'm only giving you one R. The R is telling us that we need our pressure in atmospheres, but our pressure is in millimeters mercury. So for pressure, we're going to do 843. And what's the conversion for pressure to atmospheres? 760. So we'll divide it by 760. So again, to set up my problem, I'll set this one up just so you can kind of see what I did. All right, so for my pressure, I'm going to put in 843 over 760. That's atmospheres. Times my volume, which is what I'm trying to find out, equals my moles, 4.83, times 0.0821. Let me erase that to get that out of my way. Times my temperature, which was in Celsius, so I'm going to go 20 plus 273. All right, so I'm going to take that and I'm going to move it under here. And our volume should be in liters. All right, and I believe this is the last one. Yeah, because I'm doing it inside the equation. I'm showing you that you can do it all in one place. It's just you don't have to. 843 divided by 760 is going to be 1 point something. 483 is right here. That's my moles. This is my N. This is my R. This is my T. This is my P. All right. I think I have just two more that we're going to identify. Atmospheric pressure on the peak of Mount Everest can be low, which is why climbers need to bring oxygen tanks for the last part of the climb. If the climbers carry a 10-liter, that's the volume, 10-liter tanks with an internal pressure of 3.404 times 10 to the 4th millimeters mercury, that's a pressure. What will the volume be? That's another volume. What will the volume of the gas be? What will be the volume of the gas when it is released from the tank at a pressure? That's a P2. So we have a P1, we have a V1, we have a P2, and we want to know V2. Which person is this related to? This is, come on. This is Boyle's, so we're going to use this equation. So we're going to use P times V equals P2 times V2. And just plug in your information. All right, again, I'm not so much worried about solving it right now. All right, so with that, with that stated, what I want you to do right now is you can go ahead and start working on that. I do have another review sheet that'll just kind of key you into a few things. But again, I really want you more working on these problems and trying to solve these, not so much the ones that we put on the board.